In today's session, we would be seeing how to bootstrap a regression model. So, specifically we would be seeing the application of bootstrap in context to linear models. Now, there can be basically three ways in which bootstrap can be applied in context to a linear model. The first is bootstrap based on residuals, where the bootstrap is only limited on the residuals. So, we resample the residuals and create new bootstrap samples and perform the analysis. In the second case, we bootstrap the rows of the data, and that is called the paired bootstrap. So, basically we bootstrap both y as well as the x or the explanatory variables associated with the response y. Finally, there is something called the external bootstrap. So, in this session we would learn about these three techniques, and we would implement the bootstrap technique, particularly the residual based bootstrap technique and the paired bootstrap technique in R using the boot package. Setting: assume that the linear model yi is xi transpose beta plus epsilon I runs from 1 to n, where yi is the response, xi is the p cross 1 vector of explanatory variables associated with yi, beta hat is the p cross 1 unknown vectors of regression coefficients, and epsilon I is the random error or assumed to be independently and identically distributed with 0 mean, that is expectation of epsilon I is 0 and variance of epsilon I is sigma square. Now, three types of bootstrap procedure are commonly used in context to the statistic theta, which is a function of beta. So, we assume theta is equal to g of beta. The first is bootstrap based on residuals. So, here the model that we consider is beta and f epsilon. F epsilon is the unknown distribution for epsilon, and this is estimated by the pair beta hat and f hat epsilon, where beta hat is the ordinary least square estimate of beta, which is x prime x inverse x prime y or x transpose x inverse x transpose y, and f hat epsilon is the empirical distribution, meaning that here we put mass of 1 by n to the residuals Ri minus R bar, where Ri is the residuals, which is nothing but yi minus xi bar beta hat being the least square estimate. Now, generate IID data epsilon 1 star, epsilon 2 star to epsilon n star from f hat epsilon. Define yi star, which is xi beta hat plus epsilon I star. So, xi beta hat is the predicted observations from the fitted observations from the least squares, and to that we add the IID errors that we generated from f hat epsilon. Now, we have a pair of observations which looks like yi star xi. From this pair of observations yi star xi, I runs from 1 to n, we can generate beta hat ls star or beta hat star, which is the least square estimate of the data, but now the data has changed from yi to yi star, the xi's remain fixed, and from there we can find what is theta hat ls star, which is nothing but the bootstrap analog of theta hat, which is equal to g of beta hat star. Now, note that expectation under star, that means expectation under the bootstrap epsilon I star is 0, meaning that expectation of beta hat star is x prime x inverse x prime expectation of y star, Now, expectation of y star can be written as expectation of x beta star plus epsilon star, and that is nothing but beta hat, or rather x beta hat plus epsilon I star. So, that is nothing but beta hat only. So, here expectation of beta hat star is equal to beta hat. Similarly, variance of beta hat star comes out to be sigma hat square x transpose x inverse, where sigma hat square is variance of epsilon I star, which is 1 by n, I runs from 1 to n, r I minus r bar square, or the residuals square. Now, the paired bootstrap. Now, here we assume that the data is y I x I transpose, I runs from 1 to n is I I d, the same setting as above, but the model here is a joint distribution of y I and x I, and that is estimated by the empirical CDF putting mass 1 by n to y I x I star, x I transpose, I runs from 1 to n. So, the bootstrap data are generated from the empirical distribution. But there is a problem, and the problem is that the bootstrap analog of x star, but there is a problem, and the problem is that the bootstrap analog x star of x may not be of the full rank, because it does not guarantee that x star should be of the full rank. So, one can use a generalized inverse, otherwise it is difficult to obtain the estimate beta hat star or beta hat star, which is the bootstrap estimate of the regression coefficients, but it is more computationally convenient to use the form beta hat star is equal to x star transpose x star inverse x star transpose y if lambda star is greater than equal to lambda by 2. Otherwise, use the normal beta hat least square. That is, okay. So, here we have introduced lambda star. What is lambda star? Lambda star as well as lambda are the smallest eigenvalues of x transpose x star transpose x star. So, that is the bootstrapped x and x transpose x respectively. So, lambda star is the smallest eigenvalue of x star transpose x star, while lambda is the smallest eigenvalue of x transpose x. Now, it can be shown that expectation of beta hat under this bootstrap setup is more or less equal to beta hat, and variance of beta hat under bootstrap setup comes out to be the form given below. The third thing that we can apply in context to this is called the external bootstrap. So, here EI, I runs from 1 to n is assumed to be IID sample from a distribution with mean 0 and variance 1. Then the bootstrap data are generated by setting yi star is xi transpose beta hat, which is the least square estimate, plus a ratio of the absolute value of the ith residual and square root of 1 minus hi, where hi is the hat matrix, into ei star, where ei star is obtained from the mean 0 variance 1 distribution. Then beta hat ls is simply obtained in the same way, treating yi star and xi to be the data. So, that becomes x transpose x inverse x transpose y star. Now, since the distribution of ei star can be independent of the original data, the procedure is called a external bootstrap. And here also it can be seen that under the bootstrap, expectation of beta hat star is equal to beta hat from the ordinary least squares, and variance of beta hat star has this particular form. So, now we would be seeing how to implement this bootstrap in R. We would be using a package called the boot package in R. To illustrate the application, we would be using the survival data. The survival data is in the package boot. So, if we write here library boot, that installs the library boot, and then data survival calls the data. The scatter plot of the survival data is shown here, and the theoretical relationship between survival rate and the dose is exponential roughly. So, a linear regression applies to log survival explained by the dose. So, here y is log survival and x is dose. Now, if you see the scatter plot, the case 13 is a clear outlier having the value 1410, the x value 1410. The least square estimate of the slope is minus 0.0059 using the entire data, while the least square estimate for the slope when we run the same procedure excluding the 13th case comes out to be minus 0.0078. So, to illustrate the effect of an outlier in the regression, we resample the cases. That is, here we perform the paired bootstrap. And how do we resample it? We create a function called surf.func, which is function of data and I, and then d is data I, and d.reg is lm log d $surf $d $dose, and we just extract the coefficient by coef d.reg. After defining this function, we use the boot package. The boot package has a function called boot which does the bootstrap. So, boot survival comma surf.func are equal to 999. So, we have given here 3 arguments. One is survival, which is the name of the data, surf.func, which is the function that we are going to run on this data, and r equal to 999, which is the number of times we are going to run this function, and each replicate of the function stores the slope and the intercept from the data. Now, if we draw a histogram of the observed the bootstrap slopes or bootstrap estimate of the slopes, we see that the histogram has clearly 2 modes, or rather the histogram can be divided into 2 groups. So, one group or the group in the left is the one which are based on samples which does not have the 13th observation, while the histogram on the right are based on those bootstrap samples which have the 13th observation 1 or more times. Now, there is a utility plot called jackknife after bootstrap, which shows the effect of t star minus t, that is the bias of resampling from data sets from which each of the observation has been removed. So, if we use the command jack.after.boot surf.boot and index equal to 2 means we would be, because surf.boot is storing both the intercept and the slope. So, index equal to 2 denotes the slope. So, the vertical axis shows quantiles of t star minus t for the full sample, and they are plotted as horizontal dotted line, and without each observation in turn is plotted against the influence value for that observation. And if you see, the influence value 13 is pretty far off from the other influence values. That means, the case 13, deletion of case 13 has a very strong effect. Now, we can perform the same code using the bootstrap of the residuals only. Now, to do that, what we can do is we can use fit lm log survival $surf explained by survival $dose, that is surf explained by dose for data survival, or log surf explained by dose for data survival, and we store in fit, and then we compute the residual and the fitted values and store it in res and f, create a new data which is data.frame f and res, define the function that needs to be run on the data, which is lm log data $serve explained by data $dose, and we want to extract the coefficients out of it. And the simulation function here is function data MLE. So, what happens is we are now creating this serve value by taking the fitted value and then resampling the residuals with replacement equal to true. And since the residuals, the fitted values are in the log scale, because we had used log serve explained by dose, we are taking a exponential of that, and then we are using once again the boot function, specifying the data to be survival, and the function that needs to be run is serve.r.fun, and using the sim equal to parametric in the boot call. And once this is done, we get the effect of the outlier on the intercept and the slope. In today's session, we have learned about bootstrapping linear models. So, we have learned the three techniques that can be used in context to bootstrapping linear models. One is bootstrapping the residuals, one is bootstrapping the observations by itself or the rows by itself, and the external bootstrap. We have also implemented the idea of bootstrap in context to regression when the data has an outlier. In the next session, we would be again using bootstrap in context to regression, but this time we would be using our resistant regression method called the least mean square or LTS. Now, in R, for LTS, the standard errors of the regression coefficients are not generated. So, we shall be using bootstrap to see how we can generate the standard error of the regression coefficients, and once these are generated, one can test for different hypotheses concerning the regression coefficient.